the pseudo-random number generator gives us a sequence of independent uniform deviates. But in Monte Carlo simulations, we need samples from all kinds of distributions, discrete, continuous, including dependent samples, samples from joint distributions. So in this lecture today, in our second lecture on Monte Carlo simulations, we are going to discuss how to generate continuous and uniform deviates from the sequence of IID uniforms, and then discuss how to get dependent samples, and finally a brief discussion on the need for variance reduction and how it might be achieved. So let's start with generating continuous variates from a sequence of uniform random numbers. The inversion method, it's the most general and very powerful method, and the theorem states that if I have a uniform deviate and if I am able to invert that through a continuous CDF f, then the value that I get after the inversion is distributed according to the distribution f itself. The proof is straightforward. It can be found in any textbook, but let's look at it pictorially. So what you see on the left part of this figure is the uniform PDF. So FU is the uniform PDF, and the values of U take between 0 and 1. So it's in this range, in that rectangular block on the left, that the random number generator samples from. So let's say the first sample is U subscript 1. So that U subscript 1 is now used to invert through the distribution function f. So on the right you have x and its CDF f, the red line, and so U subscript 1 is inverted through the function f, and what we get is x subscript 1. The next one, suppose that is generated is U2, and again by inverting the function f, we get x2 on the x-axis. Likewise x3, x4, and so on. So this would give me a sample from the distribution f by starting with a sample of uniform deviates. Now, as I said, this is a very general method, but the only shortcoming is that it's ideal for those distributions that can be inverted in closed form, but there are many which are not invertible. For example, the most famous being the normal distribution. We can invert it numerically, but it's no closed form analytical expression for the normal inverse. We'll discuss generating normal samples later in this lecture. So once we are not able to invert the distribution function, then obviously numerical approximations are required, and it slows down the process somewhat and may raise convergence issues. So other methods are also used in place of inversion, but where possible, inversion is the ideal choice. Let's now work through an example in which we simulate the exponential random variable. So let's say the job is to generate x from the exponential distribution with parameter lambda. So the steps would be that we first generate u from the uniform distribution and then invert the exponential CDF, which is well known, and the inversion would give me x as minus 1 over lambda times log of 1 minus u. Now in many texts and in many codes you will see that it's minus 1 over lambda times log of u, because if u is uniform random, then 1 minus u is uniform random with the same density. So we actually say one operation if we just start with u, and instead of subtracting u from 1. So then this x that we get would be the desired exponential deviate. Here I have this small MATLAB code. So let's say we are generating 100 exponentials, and so the counter goes from 1 to n, and for each of those I generate one uniform by the command rand and subtract that from 1. I did not use that shortcut that I mentioned, and taking the log of that and multiplying with negative 1 over lambda gives me the desired deviate x, and then I can use that x for whatever purpose I have in mind. Let's look at it pictorially, and here I have a small movie of 100 samples being generated. So on the y-axis you see the uniform deviates being generated one by one, and corresponding to that point we are reading off from the red line, which is the CDF of x, the exponential CDF, and for each of those black plus points we are reading off the corresponding values of x in the x-axis. So this is the application of the inversion method. Now, as you can see clearly that the blue points are generated, they look pretty much well dispersed on the y-axis, as they should be. They're coming from a uniform sample. But because of this particular inversion through that red line, clearly you see more points near 0. They are more dense there. That's because the exponential density is exactly that. It has its highest value at 0 and then falls off exponentially with increasing x. So it's clear that this is how we can reproduce, or we can sample from the exponential. If the red line was some other CDF, Gumbel or Weibel or anything else, then obviously the points on the x-axis would be different. So I would then be generating points from that particular distribution.